normal case, so that means the n exists. Okay, and here we are given r vectors equal to 3. Okay, so this is in IJK coordinate systems and with the unit du, and v equal to minus 2 square 2 and square 3 2 square 2 and 1 square 2, and in IJK geocentric coordinate systems with the unit du tu. Okay. Here we are given actually the two numbers, the positions and the velocity. We can measure it. Actually, GI, they have this kind of monitoring data every day. So here we say the given actually they can be measured. So we want to determine the 6 orbital elements. So we simply follow those kind of calculations to just calculate. So here we calculate h, the angular momentums. So do you need a graph? I don't have graph. We see. Okay, so we simply plug in here. So it is I, J, K. And then we plug in, so that is 3 squared 3 over 4, 3 over 4, 0, and minus 1, 2 squared 2, squared 3, 2 squared 2, and 1 squared 2. Okay, and do you know how to implement this? Probably you can try is this. I'm going to mess up, okay, so you just look at this carefully. So take this as a pivot, and you do this calculation plus and minus. Okay, so that will be 3 over 4 times squared and minus 0. So this is the I component. Okay, and J component basically taking this as the pivot. So basically this is the minus and this is plus. Okay, so that is minus 4 squared 2, 3 squared 3, and plus k. K will be the same thing, multiplications, minus, so 3 squared 3 over 4 times squared 3, 2 squared 2, minus 3 over 4 times minus 1, 2 squared 2. Okay, or otherwise, because I don't have a TI, I don't have a TI calculators. I don't know whether that calculator have this kind of function. Do you know what I'm saying here? Yes, right. Otherwise, I will make another example for you. No, okay, good. So this one will be square 2, 3 over 4. 3 squared 3 over 4, 3. Okay, so 3 over 4 squared 2 and 3 squared 3 over 4 squared 2, 3 over 2 squared 2. So the unit is du cubed, tu squared, tu. Then we calculate, we determine E, and E from that equation 1 over mu and V H minus mu over R times R. So that one, do the calculation, and that is square 3 over 4, 1 over 4, and 0. Okay. So again, here that is the vectors we always express in IJK coordinate systems, and again, you know that is the IJK coordinate systems, okay? So that means this is the I component, J component, K component. Yes?
Is the J component supposed to be negative, or does that negative go away? It's because it's negative and 1 above that.
Oh, yes. Thank you. This should be negative. Thanks a lot. Okay, so therefore from here we can determine E is the magnitude of this vector is going to 0.5. Okay, and so from here we can determine P equal to h squared divided by nu, and h squared is simply this x vectors square, and divided by mu is 1. Here we take the du/tu system, so that is equal to 1. Okay, so from here we can determine P equal to 2.25 P. Okay, so here we have the two things. Then that is the first two elements. Then we can determine the continue on that one. So we can determine. So that's a P and E. We determine. Then we determine. How about I? So cosine I equal to, we follow up, that is the magnitude of h k and h dot k. And h has magnitude, we can determine h has a magnitude, how much? 1.5. And k is the unit vectors of the geocentric coordinate system that has a magnitude equal to 1. And here h dot k simply is the third component, 2 squared over 2. Okay, so that one equal to this one. So therefore, I will be equal to r cosine 1.5. Not 1.5, 1 over square 2. Okay, so this one is 45 degrees. Then we determine the omega. Cosine omega equal to I n. If you don't have, say, if we don't have those kind of the formula or cheat sheets available, the best way is take the textbook or print out the good page of the slides and then working on the figures. From there, you should know which angles, which cosine you need to take care of. So for this one here, the I is 1. The n vectors, we need to determine the n vectors. What is n? So here I need to determine n first. And n is the vectors we put there, I, j, k, and 0, 0, 1, and n equal to k over h. Let me just copy that. K cross h. So here we do the calculation, that is square 3, 4, not square 3, 4 square 2, and square 3, 1, 0. Okay. So here we have n. So here we can determine the magnitude of n. So therefore n has the magnitude equal to 3, 2, square 2. Okay. So here is 3, 2, square 2. And I dot n, I is 1, 0, 0, and n vectors is 3, 4 square 2, square 3, 1, 0. Okay, I simply implement the whole calculation. So that one is square 3 over 2. So therefore, the omega is a cosine square 3 over 2. Okay. So now we come to check this one. See if nj is negative. For nj, n is our vector, that is the j component. And here the j component of n is positive. So basically here we don't need this kind of the handling. So whatever your calculator come out, you just take that number, and that one equal to 30 degrees. Okay? And then we determine omega. Omega, and again, cosine omega equal to E n, E dot n. Okay, so here we plug in all the numbers, and let me scale up the E equal to 0.5, and we calculate it. So basically here we have everything, so here is 1. So here omega equal to r cosine 1. And again, we need to check if this one we need this kind of handling. So we want to see if the component of k component of E vectors, which is 0. So that's okay. So simply we take whatever the calculated result, and that one will be equal to 0 degrees here. Okay. So the last one we determine mu, the true anomaly. The true anomaly is this cosine nu equal to r dot E and r E. Okay, we plug in everything here, then that is 1. So nu equal to r cosine 1. And again, we need to take care of any spatial situations. And so see if we have this situation happen to our case. R dot V equal to, because R dot V for this case is greater than 0, so that is in the upper portions of the orbit. So we don't need exception handling. So whatever your output is, you take it from your calculators, 0 degrees. Okay? So under these situations, and let me see how can we do this one. So say here we have our the orbital plane. So I is this one. And so PE, so E is 0.5, definitely, that is the elliptical orbit. So we determine I is 45 degrees, so orientation, what is I? I is the, let me open up. I'm going to overlap the pictures with the numbers because we have all the numbers here. Okay. So hopefully you can see we basically refer to the symbols here. So I is the inclinations of the orbital plane. So here is the equatorial plane. So I is in 45 degrees. So right now it's 45 degrees. So 45 degrees, that should be in gold. Should be in this way. Okay, 45 degrees. So in 45 degrees with the equatorial plane. Okay. And then what is omega? Omega is 30 degrees. Omega is the plane. So for example, this is a line of nodes. Okay, for example, if you see this is a line of nodes, so that is in about 30 degrees about here. And right now the inclination is in 45 degrees. So 45 degrees, that should be in this way, okay? And then omega. So what is omega? Omega is measured from line of nose to perigee axis. So that is the 0 degrees. So I need to modify. And I don't have a water except the water in my mouth. So basically here, let me show the new, this means omega equal to 0 degrees. That means perigee axis is in the n direction. So here that should be in this way. Can you see it? So right now the orbital, this again, this is an equatorial plane. So that's the inclination. So right now I'm trying to hold in this way. And then the true anomaly is in 0 degrees, so that means right now the object is right here. Of course, the orbit here I couldn't expand, but you need to imagine the orbit is larger than the equatorial plane. Basically, that is pretty much is try to imagine expanded this one, then that object should be there. So that is kind of the visual sense, the sense of this kind of orbits. Okay. So then coming back Wednesday, we will have another example when n does not exist. So that time we will come up with this figure. Probably we don't have those things anymore. Then we see how can we proceed. Okay, thank you.